Hello. In this video, I'll walk you through my implementation of the token. Mintable ESE -20 token with dividend distribution. Built on Solidity 0.7. I'll show you the contract implementation, how the tests work, and the security analysis I performed on top of the required unit tests. Let's start with token soul. A contract implements three interfaces: IEC20 for standard token functionality, immutable token for minting and burning with ETH backing, and eDividends for proportional dividend distribution. At the top, we have the do not edit section with the state variables that were predefined by the challenge: total supply, decimals, name, symbol, and the balance of mapping. This is safe message for on Solidity 0.7, which doesn't have built-in overflow protection. Below that, define 6 events: transfer, approval, mint, burn, dividend recorded, and dividend rate. These provide unchangeable. For state management, I have the allowances mapping for ERC -20 approvals, a drawable dividend mapping that tracks how much each address can claim. And then the key data structure, as address are recalled holders paired with one index mapping. This is a swap and pop set that gives us all of one insertion and removal folders. I created 3 modifiers to keep the code clean. Required ensures MSG, values greater than 0. Has sufficient balance checks the standard's token balance, and has sufficient allowance verifies the standard's approved amount. These require statements throughout the contract. The most important design decision is the holder tracking. The @holder function checks if the account is not already tracked and has non-zero balance, then pushes it to the array and stores its one based in the mapping. The remove holder function uses swap and pop. By removing a holder, it swaps them with the last element in the array, updates the index of the swap holder, then pops the array. This avoids the gas cost of shifting elements, which will be O of n. Instead, both add and remove a constant time operation. This is critical because dividend needs to iterate over holders. So we need the array to be compact with no gaps. The mint function is straightforward. It requires ETH value modifier, adds the MSG value to the color's balance and total supply, then registers the color as a holder. The burn function is where security matters most. It follows the checks effects interactions pattern. First, it reads the balance, then zeroes it out, decrements total supply, removes the holder from tracking, emits the event, and only then makes the external call with dash transfer. This ordering ensures that even if there was a re-entry that. On top of that transfer only forwards 2300 gas, which is not enough to execute any meaningful re-entrant code. The record dividend function takes and distributes it proportionally. It caches total supply and the holder's length, then looks through each holder, computing their share as MSG value times the balance divided by supply. This gets accumulated in the withdrawable dividend map. An important detail: dividends are assigned to addresses, not to token positions. So if someone receives dividends and then transfers their tokens, they still keep their accrued dividends. This is by design and masters the test expectations. The withdraw dividend function also follows C. It reads the amount, zeros the balance, it reads the event, and only then calls transfer. This prevents double withdrawal via reentrancy. Let me run the hard hat test. These are the 11 original tests from the challenge that validate the core functionality. All 11 tests pass. They cover default values, minting, burning, direct, and indirect transfers, holder tracking during mint, burn, and transfer operations, dividend compounding, withdrawals between payouts, beyond the required hard hat. I built a comprehensive fraud test suite to achieve 100% code coverage on token. So the unit tests copy every public and external function, including edge cases like zero value transfers, self-transfers, and I also wrote 7 first tests with 1,000 randomized runs. Each use property-based testing to verify variants like mint, then burn always restores all balances to zero, transfers always preserve total supply, and dividends are always proportional to holdings. The invariant tests use a handler contract that simulates random use actions, minting, burning, transferring, approving, and recording. 8 invariants I checked after every crawl across 256 runs with a depth of 128, totaling over 32,000 function calls per invariant. Key properties verified include total supply consistency, solvency, and that every tracked holder always has a non-zero balance. Finally, 13 security tests cover specific attack vectors, reentrancy on burn, and withdraw dividend, holder list deflation, val zero value transfers, dividend dust accumulation from integer division, and gas consumption with infinity fold. Running forge coverage confirms 100% coverage on tokens. So all lines, statements, branches, and functions are covered. I also set up a GitHub Actions workflow with 4 parallel jobs, hard hat tests, forge tests, with side profile for extended fuzz, and invariant runs, slither static analysis, and Solin linting, all 4 jobs passing SEP. The slither analysis found certain findings with 0 exploit vulnerabilities. The only high severity finding is a false positive on the MSU value loop detector while being read inside the loop. But in our case, we're using it for arithmetic to compute proportional shares, not send the E's in the loop. The full load findings are missing zero reduce, checks on burn, and withdraw dividend. These are accepted risks since the caller explicitly provides the destination address. The remaining findings are informational items about Solidity version and optimization suggestions blocked by the. To summarize, the token implementation uses events, modifiers, netspec documentation, the CD pattern for reentrancy protection, and an efficient swap, and POP data structure for holder tracking. The test suite includes 110 forge tests, plus 11 hardware tests, achieving 100% coverage. Slither confirms zeroed it exploitable vulnerabilities. Thanks for watching.